Day 145, Kirchhoff's laws, homework, problem number 42. This problem actually has two solutions. Let me work through them. Once again, when we're dealing with Kirchhoff's laws, we need to look at and assign currents, the most probable current flow. For example here, the battery on the left, the 12-volt battery, is trying to push current. Let's call this point up here, point A. Call this point B. It's trying to push current this way. In fact, that has to be the direction for that battery, because that battery is stronger than the other one. Depending on the resistance there, most likely for the other battery, the current is going this way, but not necessarily, and you'll see that in a few minutes. But that battery on the right, the 10-volt battery, is trying to push current in the direction of that red arrow I just drew. And if this is the case, if this in fact is the direction of the currents in those two branches, then the current in this middle branch from A straight down to B must be in this direction. And I'll call these, let's call this, say, I sub 1, current in the first branch, I sub 2, current in the second branch, and I sub 3. Actually, it tells me now in the problem that assuming there's a 1 amp current in for I sub 2, in other words, I sub 2 is 2 amps, or 1 amp, so this is 1 amp over here, 1.0 amps. That means this resistor, this 2 ohm resistor, does, if the current is indeed going that way, has a voltage of 2 volts. And indeed, in that right-hand loop, let me label these. Let's call this C and D. If I officially go around that loop from A to B to C to D, and I think you can see this probably even without me writing it down, but I'll write it down. Loop A, B, C, D, A. If I travel in that direction from A to B to C to D, the nice thing about taking that particular path is it lines up, the loop lines up with the current arrows, which makes everything the traditional conventional negative resistors, voltage, and the battery is pointing in that direction, so that will be a positive 10. In other words, the voltage of resistor number 4, I'll call that V sub 4, V sub 4 plus 10 minus 2 for that 2 ohm resistor at the top equals 0. So V sub 4 would need to be 8 volts in that case. That's an important number, 8 volts. In other words, you can see that fairly clearly in retrospect, 8 volts here, because we basically have a positive 10 volts and then a negative 10 volts. The loop is 0. Everything's conventional there. So we have 8 volts. Now, once you know you have 8 volts in that particular branch, then you know V equals IR. V is 8, R is 4. Therefore, I3 must be 2 amps. So that's 2.0 amps right there because of V equals IR. I can write it down. V equals IR. V was 8. I3 in that branch times the resistor, 4 ohms. So I sub 3 is 2 amps. Well, once you have that, you can go to Kirchhoff's first law. If you know there's 2 amps going from A to B, and I sub 2 is 1 amp going into A at the top from the right, therefore I sub 1, which looks like I got erased, this is I sub 1. I sub 1 must also be 1 amp because I sub 1 plus I sub 2 has to equal I sub 3. I can write that down, but it's pretty basic. I sub 1 plus I sub 2 is the current going into point A, junction A. That has to equal the current coming out of junction A, I sub 3, which we just found out was 2 amps. In other words, I sub 1, unknown, theoretically, plus 1 amp has to equal 2. So blank plus 1 equals 2. So I sub 1 must be 1 amp. Okay, so now if we're looking at the loop, and we'll label this, let's say E and F. If I look at loop, and we'll go conventional again, it's pretty easy, A, B, E, F, A. A, B, E, F, A. And hopefully you're starting to see these a little bit more clearly and quickly as we go along here. If I go from A to B to E to F to A, I'm going with the red arrows, the assigned current directions that I started with. So everything would be conventional. In other words, the resistors would be negative voltage. The battery is pointing in that direction, so that's positive 12. So in other words, anyways, from A to B, that would be negative 8 volts. So we'd have negative 8. Then plus the 12-volt battery. And then minus, let's call it V sub R, the voltage of that unknown resistor, has to equal 0. So the voltage of the unknown resistor R has to be equal to 4 volts. Well, once we know it's 4 volts for that particular resistor up there, 4 volts, and we know its current, which is 1 amp from the previous situation, I can just apply VR equals IR times R of the resistance of that resistor, which I'm looking for. So V sub R is 4 volts. I sub R was the 1 amp times R, the resistance, so the resistance must be 4 ohms. So that's our first answer. You might say, okay, well, how can there be another answer? Well, let me show you. Next page. So here's the alternate solution. We have the same diagram. Let's put the same references on here. A, B, C, D, E, F. And the stronger battery must prevail. So we know for sure that current is going this way in this branch. We'll call that I sub 1 again. And in the previous problem, we assumed the other battery was pushing current up. But let's say, just for curiosity, that the 12-volt battery is enough stronger than the 10-volt battery that current's going this way in this branch. So it's in the first problem, it was a pretty good guess, but now there is an option, and sometimes these options give you alternate solutions. Sometimes the options give you the same solution twice. But in this case, you'll see we're going to get a second solution. If the current's going that way in that second branch, from A to D to C to B, not the direction we assigned in the first page here, we're going to call that I sub 2 again. And we know I sub 2 is 1 amp. They gave us that. I sub 2 is 1 amp. That was given. So if I sub 2 is 1 amp, we still know that the voltage rate there by that 2 ohm resistor is 2 volts. But now let's look at this middle branch, A to B. Which way is the current going there? Well, you can guess either way, but we know for sure actually that the current has to be going from A to B because I1 must be stronger than I2 because I1 is a bigger battery, so I1 has to be greater than I2. Therefore, I sub 3 has to be going down in this particular problem. In other problems, you may have to guess on that one as well. You don't know whether it's going down or up, so you can have another situation you have to check into. But we know that I3 in this case is going down. And here's where you run into some issues with the signs. If I look at loop, say A, B, C, D, A, whether I go from A to B to C to D to A, that's in the counterclockwise direction, or if I go in the clockwise direction, A to D to C to B to A, I'm going to be going counter to one of the current arrows I've assigned. For example, the way I've chosen right now, A, B, C, D, A, if I go from A to B, that's all well and good because I'm going with the I sub 3, that red arrow, as I walk in that direction. I'm just going to call that V sub 3 for that, the voltage of that middle branch there, which current I sub 3 is the voltage 3 for that resistor, the 4 ohm resistor right there. And as I go from B to C, from C to D in particular, I'm going with that battery, so that's still plus 10 volts for that battery because it always depends on if you're walking in your loop in the same direction as the battery's pointing, quote unquote, you get the positive battery voltage. But now here's where the tweak comes in. From D to A, normally that would be negative 2 volts. However, in this case, it's plus 2 volts because as I'm walking, quote unquote, from D to A, my current arrow, that red 1 amp current, is actually to the right, counterclockwise or clockwise, and I'm walking from D to A counterclockwise, so I'm opposite what it normally would be as a negative 2 volts plus 2 volts. So that all comes out to be 0. With that in mind now, simply put, V sub 3 has to be 12 volts. Well, that is that 4 ohm resistor, 12 volts. And if I know that's 12 volts, that's V, and we know R, and we plug into V equals IR, that means, well, I'll write it down. V sub 3 equals I sub 3 times the 4 ohm resistor times R. I'll just call it R for now. It's 4 ohms. But V sub 3 is 12 volts. This is so basic we did it in our head, but I sub 3 is unknown. The resistor there is 4 ohms. So I sub 3 must be 3 amps. All right. So I sub 3 is 3 amps. Well, that means by default I sub 1 must be 2 amps. I'm sorry, it must be 4 amps, because I sub 1 going into point A must be equal to the current coming out of point A, which is I sub 2 plus I sub 3, and that's 1 plus 3 is 4 amps. So there must be 4 amps going into point A. But we're actually doing a little bit of overkill here, because if we would have looked at this ahead of time, if I'm looking at my other loop, B, E, F, A, B, the voltage around that loop from B, E, F, A, B, if I write it down, loop B, E, F, A, B. That's kind of a nice loop because I'm going with all the current arrows. But if I start at B, go to E, go to F, I hit the battery first, which would be the positive 12 volts. Then minus V sub R, the resist or the voltage of that unknown resistor at the very top of that loop from F to A. And then from A to B straight down, it's conventional direction with the current and the voltage. So that's minus 12 equals 0. Well, what that means is V sub R, and we could have seen that coming, is 0. Well, if V sub R is 0, then if you look at V sub R equals I sub R times R itself, V sub R is 0, I sub R is 4 amps times R. Well, the only way that can work is if R equals 0. In other words, the alternate solution is this can work, it'll look like this, if the resistor is 0, you would get a situation like that where you get current flow as pictured with basically the 10 volt battery being quote unquote charged and currents flowing in the direction of the arrows here, as opposed to the first solution when R was what was it, 3 or 4 ohms, and then the other currents from the previous solution. So there was 2 solutions, R equals 0 or R equals 4 ohms, depending on the direction of current you pick for that second branch. In other cases, if you pick a different direction, you will still get the same solution twice if you're consistent with your positives and negatives. One more thing I can show you just for a little bit more practice, going back to this first scenario where we have the 4 ohm. I could have done this with either one of these, but in this case, going back to the first solution with the 4 ohm resistor, if I look at loop, let's say F, A, D, C, B, E, F. Let's go all the way around the outside. There are 4 elements from F to A to D to C to B to E to F. I can call that V sub 1 plus V sub 2 plus V sub 3 plus V sub 4 equals 0, to give my generic statement for 4 voltages that add up to 0. If I follow that loop, and once again we have some unconventionalities, because if I go from F to A, I'm good. I'm going with the current arrow I sub 1. From F to A, that would be your typical negative 4 volts. But when I go from A to D, usually that would be negative 2 volts. But if I'm going against the current arrow, which is pointing towards A, but I'm going from A to D, that would give me the plus 2 volts. That's the opposite of what we normally would have for a resistor, because I'm going against the flow of current. And then for the batteries, I go from D to C, I'm going into the positive, I'm going against the battery, so that would be opposite its normal positive 10 volts, that would be negative 10 volts. So those are the 2 tricky ones there, as I walk from A to D to C. And then back from C, B, E, and from E to F, that would be the conventional plus 12 for that battery. And that has to come out to be 0. I'm not really solving for anything here, but I'm just showing you that that's consistent. If you look at those numbers there, that says, well, 0 equals 0. So that's just a check to show you then practicing our positives and negatives, because no matter what loop you pick, you still have to get a 0 total voltage no matter which way you go around that loop or any loop that you pick. The total voltage has to come out to be 0 in all cases.